In this video, I'll be giving an overview of designing and fabricating a three-dimensional object using 3D printing technology, a process we call the 3D printing workflow. This workflow has 5 phases: modeling, exporting, slicing, printing, and post-processing. Let's take a look at each of these phases in detail and how they might be implemented in the education setting. The first phase of the 3D printing workflow involves creating or obtaining the three-dimensional object you'd like to print. This is actually the phase where the most intensive work comes in. Think about it. When you write an essay, the majority of the effort goes into writing the words, not formatting the document or clicking print. While there are more considerations for the 3D than the 2D printing process, the majority of your effort should still be directed toward what you're going to print as opposed to how you're going to print it. This is especially true in the education setting, where it's important to emphasize the design process over the final product.
A 3D model is a digital representation of an object created using specialized software. Often, the model is generated using computer-aided design or CAD programs such as AutoCAD or SketchUp. 3D models can also be obtained from an online marketplace such as Thingiverse, where individuals can share or sell their designs. Or they can be generated by using a 3D scanner to create a digital model of an existing physical object.
In a typical education project, students use software to create a 3D model that meets educator-defined constraints, whether that means designing a boat to hold a certain amount of weight, or modeling a fictional gadget based on a description from a book. For these types of projects, a great resource is Tinkercad.
Tinkercad is a free cloud-based 3D modeling application especially for beginners. Users can drag and drop shapes into the workplane and combine them in different ways to create original 3D designs. Tinkercad offers a number of features especially for classroom use, including built-in tutorials, lesson plans, and the ability to create classes where you can review and monitor student designs.
The second phase of the workflow involves exporting the 3D model as a stereolithography or STL file. STL files are sometimes referred to with the backronym Standard Triangle Language because they're basically a tessellation or mesh of tiny triangles covering the surface of a three-dimensional object. It's kind of like chainmail, but with digital triangles instead of metal rings. You don't need to have a perfect understanding of STL files in order to use them for 3D printing. You just need to know how to create one.
From Tinkercad, you can easily export a design as an STL by navigating to the upper right corner of the edit screen and clicking the export button. This brings up the option to download your design as one of 3 types of 3D files, or as a 2D vector graphic for applications such as laser cutting. You will notice a separate tab which allows you to send your file directly to a print management platform such as Polar Cloud. These services allow you to initiate print jobs remotely via the cloud and are usually designed to work with particular printer models or brands. You can do research to see if there is a cloud-based platform that works with your printer. For now, however, we'll be exporting our file the old-fashioned way. Select STL and the file will automatically download to the default location on your device. From there, you can transfer the file via email or USB, or you can import it into a slicing software for the next phase of the workflow.
One thing to keep in mind about STL files is that they only contain information about the surface geometry of an object, not color, texture, or any other attribute. So even though my model was purple in the example you just saw, the actual color of my print is going to be whatever color filament I load into my machine. In this case, green. The other thing to remember about STL files is that 3D printers can't actually print them, at least not directly. First, we need to convert them to another type of file known as G-code. G-code is a programming language used to give instructions to computer-controlled manufacturing equipment. This includes 3D printers, as well as tools like CNC routers and laser cutters. 3D printers can't read a digital model of a 3D object like an STL file, but they can understand a set of instructions telling them where to deposit material when. A special type of software, known as slicing software, is used to convert STL files into G-code instructions the printer can understand. Most 3D printers have their own slicing software optimized for use with their machine. The software I'll be using is called FlashPrint. It's designed for use with FlashForge printers like the Finder here. The basic controls for most slicing softwares are pretty similar, so once you have a little bit of experience, it's not too difficult to switch between different slicing softwares.
Once in FlashPrint, the first step is to import your STL file. You can do this by clicking the blue Load button at the top of the screen. Navigate to where the file is saved on your computer and then double-click to load. You may get a message that says your model is off the platform. Click Yes to move it back onto the platform. Now, I didn't in this case, but it's possible you'll get a message saying that there is an error in the model and asking if you would like it to be repaired. If this happens, you can just click Yes, and 99 times out of 100, that'll solve the problem. From here, you can move your model within the print area, rotate it around the X, Y, or Z axis, or scale it up or down in size. You can also add supports if necessary. I'm happy with my model as it is, so I'm going to click the blue print button at the top of the screen. This brings up this dialog box where you can adjust your print settings, including machine type, filament type, and the resolution of your print. The higher the resolution, the longer a print job takes and the more material it uses. So I recommend sticking with low or standard resolution for in-class projects, unless it's like your final entry for a design competition. Lastly, it's a good idea to add a raft or a brim to help anchor your project to the build plate. There are other settings you can adjust in Flash Print to fine-tune your project, but that's it for the basics. So click OK, and the program will generate a G-code file according to the settings you selected. And you'll notice in the upper right corner that it's giving us an estimate of how long this print will take and how many meters of filament it will use. Now, we have the option to either send the G-code file directly to your printer over Wi-Fi or to export it manually. I'm going to export or download this file to my computer, and you can see that it's a G-code file because it has this extension .gx. That file extension does vary from software to software, so sometimes it's .g or .gcode, but with the FlashForge, it's .gx. I can save my .gx file directly to a USB drive so that it's ready to transfer to the printer. Right now that I have my G-code file, I'm ready to print. So I'm going to plug my USB into the FlashForge Finder here, which is one of several ways to transfer a print job to this machine. And it's important to note that my printer here is ready to print. So it's powered on and it's loaded with the filament type of my choice. And this filament should match the filament type I selected earlier in my print settings, which in this case was PLA, and this is PLA filament. I'm also going to lay down a light layer of glue to help the first layers of my print adhere to the bed. Now, I don't need to cover the entire bed, but just the area where I think the machine is going to be printing. And I also don't need to lay it on very thick. A thin layer will do just fine. Initiating a print job of the FlashForge Finder is as simple as pressing Build, selecting my flash drive, selecting my GX file, and then clicking Build again. After starting the print, it's best to watch the machine for at least a few minutes to make sure it successfully lays down the first layers of material. If I notice a problem, for example, the material isn't sticking to the bed or the filament gets jammed, I can stop my print, address the problem, clear the material, and start the job over again. This is a good practice to teach your students as well. Set the expectation from the beginning that they need to watch their prints get started, and teach them to press stop and seek assistance if something doesn't look right. As it happens, it looks like my print is sticking just fine, so I'm going to leave this to do its thing. In general, once a print is successfully started, it's okay to leave it printing unattended, though you might want to check in on it every so often if it's a more complex print. All right, it looks like my print is done. So on this machine, you can actually just pull the whole build plate out. And then what we want to do is use a metal spatula tool, such as this one, and gently slide that underneath the print and use it to detach the print from the build plate. Next, we would want to remove any of the extraneous support material, such as a raft or a brim, like I've got on the bottom of mine. And if this proves to be too difficult with your hands, then you can use tools such as micro cutters or a craft knife. Now, for a lot of beginner projects, removing residual support structures like this might be the only post-processing that you do. But if you're interested in a more polished look, there are a number of ways to finish
3D prints, such as sanding off layer lines, painting, gluing, adding mechanical or electrical components. There are a ton of different finishing techniques out there, and they vary a lot depending on the type of material that you're working with. So take some time to research different options on the internet. Sanding techniques are a great place to start no matter what filament type you're using. So in the education setting, post-processing techniques are best saved for special projects, just like high-resolution prints. But when they are used, they can be a really great opportunity to cultivate craftsmanship and a sense of pride in one's work, and also a way to give learners a taste of what digital fabrication is like in the professional world.
In review, the phases of the 3D printing workflow are first, obtaining or creating a 3D model using CAD software such as Tinkercad. Second, exporting your 3D model as an STL file. Third, converting your STL file into printer-friendly G-code using a slicing software such as FlashPrint. Fourth, printing your object. And fifth, perfecting your print through the use of various post-processing techniques.
Now that you understand this workflow, you can use it to guide your students through the 3D printing process and set them up for success at every stage. Thank you for watching, and I wish you well on the next phase of your 3D printing journey.
This video was brought to you by Idaho STEM Action Center as part of the iSTEM Library's online database, a searchable catalog of STEM teaching tools available for checkout at locations across Idaho. You can browse available items in your area, as well as curriculum, how-to guides, videos, and more by visiting stem.idaho.gov/i-stem-library or by contacting the library location nearest you.